Across our solar system, scientists are turning their gaze far beyond Earth toward distant worlds that might just cradle life. On October 18, 1989, the Galileo spacecraft launched from the Space Shuttle Atlantis, setting course for the mighty Jupiter system. Its mission: to unlock secrets long buried within that massive gas giant and its surrounding moons. But along the way, a small, icy world named Europa caught the scientific community off guard, emerging as one of the most promising candidates in the search for alien life. What Galileo found changed everything. This wasn't just a flyby, it was a revelation. As Galileo soared past Europa, it gathered and beamed back data that stunned researchers. Clues that pointed to a vast, salty ocean beneath its frozen crust, teeming with the potential for energy and, possibly, life. To go deeper, NASA launched the Europa Clipper, a next-generation spacecraft built for a single, profound purpose: to uncover the truth about this enigmatic moon. Its mission: map Europa's icy surface, analyze its layered shell, detect the chemistry hidden below, and search for signs, any signs of life. But this isn't just another space mission, it's a turning point in our cosmic journey. A defining step in answering one of humanity's oldest questions: are we alone? The pursuit of Europa isn't simply about one moon. It's about reimagining our place in the universe. A universe that may be far less lonely than we once believed. This investigation is real, and it's only just beginning. Europa, the fourth largest moon of Jupiter. Its existence as a potentially habitable world is no longer mere speculation. It's a conclusion reinforced by decades of data. A solid scientific case for an environment that may cradle life. Europa's surface and geological structure are extraordinary, remarkably smooth, with a striking lack of impact craters. This stands in sharp contrast to more ancient celestial bodies like our own moon, which bears the scars of billions of years of meteor strikes. The absence of large craters on Europa is a critical clue. It suggests the surface is young and, more importantly, actively being renewed. This points to powerful internal geology, a relentless process of resurfacing from within. Zooming in, spacecraft have revealed incredibly complex tectonic features, providing further evidence of internal activity. Europa's surface is crisscrossed by thousands of long, winding fractures that can stretch for hundreds of kilometers. But these aren't just ordinary cracks. They're often stained a deep reddish brown, hinting at the presence of minerals or organic compounds rising from below, possibly from an underground ocean. Most remarkable of all are the chaos terrains. These are vast regions where the icy crust appears shattered into countless fragments, jumbled and refrozen into a chaotic mosaic. Imagine a massive frozen lake on Earth, shattered by an earthquake or some great force from beneath, then refrozen in a jagged, uneven state. On Europa, these chaotic regions span hundreds, even thousands of square kilometers. Features like these couldn't form on solid, geologically dead ice. They're a clear sign of internal movement. The crust is continuously deforming, cracking, and, most crucially, interacting with something far more fluid deep below. This is the evidence of a subsurface ocean. Surface clues suggested a hidden sea, but it's the data from space probes that delivers undeniable scientific proof of this vast body of water. The trail of discovery began with NASA's Voyager 1 and 2 in the late 1970s. They captured the first images of Europa's smooth, puzzling surface. An early hint that this moon was unlike any other. But it was NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, that provided the real breakthrough. Though it never directly saw massive water plumes. In 1997, Galileo recorded a phenomenon resembling a burst of water vapor. Its plasma and magnetic field instruments detected a sudden drop in local plasma density, a signal consistent with the craft flying through a column of steam. In 2013, the Hubble Space Telescope observed ultraviolet light absorption at Europa's limb as the moon passed in front of Jupiter. revealing towering water plumes up to 200 kilometers high erupting into space. Further analysis in 2016 reinforced these findings. It's estimated that every 8 minutes, enough water is released to fill an Olympic-sized swimming pool. These plumes suggest that liquid water lies directly beneath Europa's icy shell. Scientists analyzed high-sequence images from Galileo and found that the moon's icy shell rotates at a variable rate. If Europa were solid rock and ice, its crust would be gravitationally locked, spinning in sync with the core. But instead, Jupiter's relentless gravitational tug twists Europa's shell, inducing stress and movement. This is compelling indirect evidence of a subsurface ocean separating the crust from the rocky mantle. One of the most persuasive pieces of evidence came when Galileo detected an unusual disturbance in Jupiter's powerful magnetic field as it passed by Europa. This anomaly indicated the presence of an induced magnetic field generated within Europa itself. Such a field arises from electrical currents inside a conductive layer, created as Jupiter's magnetic field sweeps past. And the only material capable of producing such strong currents under those conditions is a global saltwater ocean in motion beneath the ice. This discovery has nearly confirmed beyond doubt the existence of a global salty ocean beneath Europa's icy shell. Measurements suggest that this ocean has electrical conductivity similar to Earth's oceans. That ocean, scientists believe, may be interacting with Europa's silicate mantle, just as Earth's seawater interacts with its seafloor. This process could provide essential minerals and chemicals, forming a rich chemical environment necessary for life. Heat energy comes from tidal deformation and friction, generated by Europa's continuous flexing under Jupiter's gravity. Scientists hypothesize that under-ice volcanic activity may exist on Europa's ocean floor. If true, this could create hydrothermal vents like those found in Earth's oceans. Vents that release heat and vital chemicals like sulfur, hydrogen sulfide, and metals. These form chemical ecosystems, potentially capable of sustaining life. Hubble also detected carbon dioxide, CO2, on Europa's surface, likely sourced from the underlying ocean, expelled in water plumes and broken down by ultraviolet radiation. Additionally, hydrogen peroxide, H2O2, has been observed in the surface spectra, an important compound in methanogenesis, a chemical process that could serve as an energy source for microbial life. NASA's Juno spacecraft detected atomic hydrogen and oxygen ions, indicating a significant amount of oxygen being produced through radiolysis, the splitting of water molecules by radiation. On Europa's surface, models estimate that Europa generates about 12 kilograms of oxygen every second. While most of this oxygen remains on the surface or escapes into space, a small fraction may seep into the ocean through surface cracks, offering a potential oxygen source. This increases the possibility that biochemical cycles could exist beneath the ice. Geophysical models suggest that Europa's subsurface ocean may have existed for more than 4 billion years. This prolonged duration provides a stable, sheltered environment for potential life, protected from harsh surface conditions like intense radiation and meteor impacts. Stability and time are critical ingredients, not just for life to exist, but for it to evolve and diversify. As NASA's Galileo spacecraft flew by Europa multiple times, scientists meticulously analyzed its gravitational field. By calculating Europa's moment of inertia, they inferred its internal structure. The results revealed a thick, icy shell. Beneath which lies a liquid water layer, followed by silicate rock and a metallic core. This model supports the hypothesis of an ocean separating the ice shell from the rocky mantle, acting as a buffer that absorbs Jupiter's powerful tidal forces. Detailed surface observations from Galileo included unusual impact crater structures. Unlike the sharp, well-defined craters on rocky planets, some of Europa's large craters have concentric ring patterns. Similar to what happens when an object strikes a relatively thin, solid layer and plunges into something softer beneath, producing shock waves that ripple outward in circular rings. The mechanism sustaining Europa's liquid water remains one of the most compelling aspects, although we haven't confirmed a direct connection to the subsurface ocean. Hubble Space Telescope observations in 2012, 2014, and 2016 spotted faint plumes of vapor erupting from Europa's surface. A reanalysis of Galileo's 1997 data suggests it may have flown through a similar plume. These plumes not only suggest the presence of liquid water, but point to an internal energy source powerful enough to push that water upward. Creating a direct pipeline from the subsurface ocean into space, carrying materials from deep within. The most critical factor in maintaining Europa's liquid ocean is Jupiter's immense tidal force. Europa does not orbit Jupiter in a perfect circle. Instead, it follows a slightly elliptical orbit and is also gravitationally influenced by other large moons like Io and Ganymede. As a result, Europa is constantly stretched and squeezed by Jupiter's powerful gravity as it moves along its orbit, generating significant frictional heat within its ice and rocky interior. Based on models and collected data, scientists estimate Europa's ocean could be up to 60 miles, around 100 kilometers deep, containing more water than all of Earth's oceans combined. With such a vast water volume and a stable tidal heat source, there's a strong possibility that hydrothermal vents may exist on its seafloor. Similar to those on Earth that support rich, complex ecosystems in the deep ocean. As analyzed from data gathered by the Voyager and Galileo missions, Europa stands out as a world with long-standing potential for life, a global liquid ocean that has existed for billions of years. It offers an ideal setting for chemical reactions to occur. Enabling the formation of complex molecules and the development of biological processes. Internal tidal heat and hydrothermal potential. The energy from tidal forces not only keeps Europa's ocean in a liquid state, but may also fuel hydrothermal activity at the ocean floor. Models suggest that Europa's rocky core could undergo hydrothermal reactions with seawater. These vents release heat and dissolved minerals from within Europa's rocky interior into the ocean, generating chemical and temperature gradients. This creates a rich source of chemical energy. Europa lies deep within Jupiter's intense radiation belt. Europa's ocean is believed to be salty and mineral-rich, a prime setting for the formation of complex molecules and efficient chemical processes. With all these favorable conditions, a vast and stable liquid ocean, multiple sources of energy, tidal heat, radiation-driven chemistry, and the presence of essential chemical elements. Scientists believe that potential life on Europa could take the form of primitive microorganisms, much like the chemosynthetic bacteria found near deep-sea hydrothermal vents on Earth. These are life forms capable of producing their own energy from chemical reactions, independent of sunlight or photosynthesis. To strengthen this belief, we can look to discoveries here on Earth. One of the most remarkable is the detection of unique bacteria in Lake Vostok, Antarctica. A vast freshwater lake buried under 4 kilometers of ice, completely isolated. The lake's conditions are extremely harsh, no sunlight, crushing pressure, and limited nutrients from the outside world. Yet, when it was drilled and sampled, researchers discovered microbes that had never been found elsewhere. Life endured. These bacteria had adapted to survive by drawing energy from chemical reactions with minerals from the rocks below. This supports the idea that life might also persist in similarly extreme conditions on Europa. Yet, scientific imagination does not stop at single-celled organisms. Some researchers, driven by bolder curiosity, hope to explore the possibility of more complex and even intelligent life. Could there exist an entire ecosystem beneath Europa's frozen crust, populated by multicellular organisms? Perhaps chemosynthetic microbes form the base of the food chain, feeding larger organisms, maybe even predator-like creatures similar to sharks. Or could there be a hidden civilization in those dark waters? Though still within the realm of science fiction, such ideas inspire the imagination and elevate Europa into a symbol of cosmic possibility. Each data stream, every image returned from Europa is a profound reminder of the universe's vastness and mystery. Pushing us to continue the endless pursuit of exploration and discovery. NASA's Europa Clipper mission, first light into the darkness. Europa Clipper is not just a spacecraft. It is a beacon of hope, a pinnacle of engineering and scientific ambition. It represents NASA's flagship mission to thoroughly investigate the habitability of Europa, an unprecedented effort to uncover the secrets of this hidden ocean world. Its goal is to definitively assess Europa's potential to support life, an essential and cautious scientific step. The spacecraft will collect critical data to determine whether the ocean has the necessary conditions for life as we know it. Is it warm enough to sustain stable liquid water? Are the essential chemical building blocks present? This mission is a foundational survey, a vital reconnaissance before any direct search for biosignatures can begin. Europa Clipper is scheduled to launch on October 14, 2024. A moment that not only marks humanity's continuing advance into space exploration, but also symbolizes the synergy between scientific ambition and modern technological capability. After a long and complex interplanetary journey lasting nearly 6 years, the spacecraft is expected to reach Jupiter around 2030. Once in Jupiter's orbit, Europa Clipper will not attempt to enter orbit around Europa right away. The reason is both clear and daunting. Jupiter's intense radiation environment, especially the belt in which Europa resides, is among the most hostile in the solar system. To achieve its ambitious scientific goals, Clipper is equipped with a suite of 9 of the most advanced scientific instruments ever flown. Each meticulously designed to uncover a different aspect of Europa's nature and its ability to support life. The reason: radar for Europa assessment and sounding, ocean to near source, a powerful ice-penetrating radar. This instrument will send radio waves deep through Europa's icy crust and listen for reflected signals. It will measure ice thickness from a few kilometers to several tens and search for internal structures. Like distinct ice layers, fractures, and most importantly, determine the depth of the subsurface ocean. Reason can also identify pockets of liquid water deep within the crust. EIS, Europa Imaging System, a high-circle engine imaging system with both wide-angle and narrow-angle cameras. EIS will capture the most detailed images ever of Europa's surface. Allowing scientists to map geological features such as fractures, ridges, and chaos terrains. MI's imaging spectrometer for Europa, a spectral imager that will map the chemical composition of Europa's surface. Analyzing reflected light across different wavelengths. If Europa is releasing organic or biologically significant compounds, these instruments could detect them. This may be the best way to probe Europa's ocean without drilling through its ice. PIMS, Plasma Instrument for Magnetic Sounding. This instrument will measure the magnetic field and plasma around Europa. By analyzing plasmas, PIMS will help scientists understand how Europa's ocean interacts with Jupiter's harsh radiation environment. Gravity. Radio science experiment. This experiment will use the spacecraft's radio signal to measure Europa's gravity field with extreme precision. As the spacecraft flies by, the moon's gravity will subtly alter its trajectory. By analyzing these shifts, scientists can model Europa's internal structure in greater detail. Including estimates of the size and distribution of the subsurface ocean, and even the existence of a metallic core. The expected results from this mission are far from ordinary, and its impact will go far beyond numbers and data. Europa Clipper will deliver strong indirect evidence of Europa's habitability. It will lay the essential groundwork for future missions, pointing to where we should look next and how. This is a sweeping, unrelenting investigation poised to transform our understanding of Europa and its place in the grand search for life beyond Earth. Beyond NASA's efforts, missions from other international space agencies are also contributing to the journey of exploring Europa. And other icy moons of Jupiter, underscoring the global importance of the question of life beyond Earth. Science knows no borders, and international collaboration maximizes our chances of success. For example, the European Space Agency's JUICE mission, Jupiter Icy Moons Explorer. Though primarily focused on exploring Ganymede, the largest moon in the solar system and also believed to harbor a subsurface ocean. JUICE launched in April 2023 and is expected to reach the Jovian system in 2031. Although these flybys are not JUICE's primary objective, they will provide valuable supplemental data about Europa. complementing the detailed picture being built by Europa Clipper and offering diverse perspectives from different instruments and orbital paths. This diversity of data is crucial for forming a comprehensive understanding of Europa. The future of Europa exploration opens nearly limitless possibilities. Pushing the boundaries of science and technology beyond what we can imagine today. Looking even farther ahead, a thrilling and profoundly challenging vision emerges. Sending underwater robots to explore Europa's hidden ocean directly. Imagine autonomous submersibles engineered to withstand crushing pressure and freezing temperatures. Diving into the eternal darkness of an alien ocean, swimming through waters untouched by any Earth life. These robots would be equipped with cameras, biochemical sensors, and sampling instruments. To collect direct data and imagery from the environment, potential hydrothermal vents, and most importantly, any life that may exist there. This journey is not just about Europa. It is a relentless pursuit, a deep yearning to better understand the universe we belong to. In humanity's great adventure to uncover the secrets of the cosmos, Europa has emerged as a leading target, with compelling and increasingly strong evidence of the necessary conditions for life. This search is not a single leap, but a series of vital stepping stones. Each mission plays a pivotal role in answering the mystery of life on Europa and in deepening our understanding of extraterrestrial environments. NASA's upcoming Europa Clipper mission is a powerful testament to this commitment. While it may not directly touch life, the data Clipper gathers will serve as the strongest indirect evidence yet, a detailed roadmap pointing the way toward bolder exploration efforts. Following Clipper, our vision turns toward Europa Lander, an ambitious mission concept in development by NASA. It is not only about identifying favorable conditions, but about searching for direct evidence of life itself. These missions are not merely scientific endeavors. They represent an expansion of our understanding of life in the universe and the possibility of its existence under conditions we once believed to be impossible. Could life thrive in places devoid of sunlight, sustained by chemical energy from deep within a planetary body? If Europa holds the answer, yes, it would shake the very foundation of our assumptions about Earth's uniqueness and humanity's solitude. This would not be just a scientific discovery. It would be a fundamental shift in how we perceive our place in the vast universe. And what limits the human drive to explore can truly overcome. Each mission, each piece of developed technology, every bit of data gathered may be richer and more varied than we ever imagined. The journey continues with unrelenting curiosity and humanity's boundless thirst to explore.